We're going to start off by talking about sequences. Sequences. Now, you might say, Dan, what the heck is a sequence? So let's get into this, okay? So a sequence is a function. Now, for those that aren't familiar with what a function is, now, I always like to conceptualize it as a machine. It's a very computer science-y way of thinking about a function. Is you imagine I have a function, and I don't know, maybe it has a name. Maybe we'll call it F. That's its name. And it takes an input, and it produces output. So the input here for the definition of a sequence is going to be an integer. And as output, it's going to give me a term in that sequence. So it gives me an integer, spits out a term. So each one's going to be associated with an integer. So let me write this out for you. So you just imagine it like a machine. Every time I give it an integer, it spits out a term in something we call the sequence here. So a function whose domain, that means we're talking about what you can feed into this machine, whose domain is either, and I like to be this way because some people have different definitions for this, but they all are equivalent with each other. It's just, I like to be rather generous. Either all the integers between two given integers. So you can imagine you have like a first term and a last term. These are going to be dictated by integers, and every integer between them, these counting numbers, are all going to be between these two given integers, or all integers. So these are your numbers like 0, 1, -5, positive, negative, 0. These are integers. Or all integers greater than or equal to a given integer. So for example, I could have a sequence that's going to be defined by, say, it's going to have each integer, say 2, 3, 4, 5, 6, 7, 8, 9, 10, and each one will have some integer, and each one will give me some output, a term in the sequence. So usually the way this gets represented is as a set of elements written one after the other, like this. So I have like AM plus 1, AM plus 2, AN minus 1, AN. So notice in this case, I wrote it so it's given with two integers, where M is the lowest one and N is the higher one. So just some terminology that I'll use very often for today's lesson. This is often referred to as a term, like I said. This is a term in the sequence. So each one of these is a term in this sequence. You can imagine M being a 0 and N being any one integer as well. So if you're wondering, Dan, where exactly do you see like these two sound like two different things, but actually all you have to do is just slide this window, or you can just redefine the function so it maps it onto the positive integers. Some people define it that way too. The point is, it's just some sequence of usually numbers. So I have a term, and you might ask, okay, so what is k here? This is often called its index or subscript. And unless otherwise stated, just assume k is an integer, okay? Just assume it's some integer. M, so the M here, this is the initial term. And if there exists this AN here, because keep in mind you can define it such that it could be on all the integers, for example, meaning that it's actually, this sequence never ends. This would be called the final term. So I must stress that you can have what we call an infinite sequence. That would be where you have like AM plus 1, all the way on and on and on. This is so this would be an example of a finite sequence. This would be an example of an infinite sequence. I was about to write integer, but it sort of melted into infinite, okay? Let me just fix that. So we got infinite sequence. So that's just some terminology. And we haven't really seen any examples. Let me give you some examples of sequences. I'm sure you've probably seen some sequences before. For example, here's some well-known ones. So you might think of like the even integers. In fact, let's say the even positive integers. So that would be things like 2, 4, 6, 8, 10, and so on, where in this case the terms would always look of so they'll take this form. AK is equal to 2 times K. And this is for every K greater or equal to 1. These are all your positive even integers. And this is actually a general way of representing any one of the terms in the sequence. So every time it's just whatever that index is or subscript is, you multiply it by 2. That's how you can generate this. So if you ever wanted to describe this as a function, notice you just give it a name, like f, and you give it k as input, and what it outputs would be 2 times k. Hopefully this kind of connects a lot of these pieces here. So likewise, I can define the odd positive integers as well. So these are your odd numbers. So we have 1, 3, 5, 7, 9, and so on. Notice that these are both infinite sequences, by the way. The general term here, well, to get an even positive integer, all I do is I take whatever the index is and I multiply it by 2, right? Now, notice that for those that are acquainted with the idea of parity, that every integer is either even or odd, right? So if you know that every time I want to get an even positive integer, I just take 2 times this. If I want every other one, which means we don't want a multiple of 2, what can I do? Are any ideas? Any ideas at all? Don't be shy. I'm just going to put that on over here. So are there any ideas? Well, notice that if I put in 1 into this, I get 2. I put 2 here, I get 4. I get 3, I get 6. Well, here's one suggestion I have for you. One suggestion. Well, you know, this will make an even integer, right? Well, what if I add 1 to it? Well, this will throw it off always by an offset of 1. So I end up like when I go 2 times k, I get an even integer, right? I'm just gonna add 1 to it just to kick it 1 step over, okay? And that'll give me an odd integer. And in fact, if you look at this, this is actually the form of any odd integer. So you can say this for every k greater or equal to 1. Actually, is it 1 or is it 0? Well, let's think about it. 2 times 1 plus 1, that would give you 3. So this isn't supposed to be that, it should be 0. Notice that if you try k is 0, you get 2 times 0 plus 1. Notice the plus 1 kicks it in the direction, making it slightly bigger, right? So I start k a little bit smaller. Now you might look at this and say, Dan, that's not really impressive, right? Well, let me just kind of tie this all together where the heck this came from, okay? So let's see here. So you might be asking, okay, so what's this and what's that? Those are actually the definitions of what an even and odd integer are, right? An even integer is one for which it is an integer where you could write it in this form, where k is some integer. Likewise, an odd integer is simply an integer of this form where there exists this integer right here. So it shouldn't be very surprising. These are literally how you could define these things. So this is just generating a list of these. And the list is a sequence. The point is that the sequence just goes on forever. But you can always keep in mind, you can always define the sequences to be finite instead for some final term. So you can imagine you're giving me like the first 100 even integers or the first 100 odd integers. Let's think of something a little bit more interesting. Let's think of the square numbers. I always like to take these opportunities to do my flex here. Square numbers. So, as the name suggests, each number in the sequence here, so the first term will be 1 times 1. So I'm gonna 1 times 1. Okay, now I'm gonna take 2 times 2, that's 4. So I'm gonna take the square of each index here. So it's 1 squared, 2 squared, 3 squared is 9, 4 squared is 16, and so on. So the general term, what should that look like? Well, it's quite simple, right? It's just k squared, where k is a term. Sorry, I'm getting very excited here. It's just k squared. And to remember, it starts off at 1. So this would be for all k greater or equal to 1, right? Sorry, my writing is sort of melting over there, okay? I put it in the microwave a little too long. So this is what a sequence is. These are some examples of sequences. Very often when we describe performing some sets of operations, sometimes we define them on a sequence like this. So I'm going to include in my notes here some examples of things to keep in mind whenever you're getting creative with formulating sequences like this. So these ones weren't terribly surprising because they're all just based on the definitions of what they are, right? So the first one was, that's how you define an even and positive integer, that's an odd positive integer, and that's a square number. You can define all sorts of other types of number sequences. In fact, one place that I would encourage you to check out is oeis.org. This is the online encyclopedia of integer sequences. You can find all sorts of wild number sequences. So if you're looking for a lot of different sequences, in fact, you can even type in numbers and say if you're not sure what sequence it is, like say I'm running into a bunch of numbers and you're not sure exactly what they are, you could try searching using your sequence. So you just start typing in your sequence and you see if it matches up with anything that's already there. And so people add to this big database of integer sequences. So this is sort of it's very interesting. In fact, I'm not sure if it still exists. It's been a while since I've went to this website. But they have a feature where you can play the sequence as a MIDI music file. So if you ever wanted to hear what the Fibonacci sequence sounds like, or any one of these that I've written up here sound like, you can do that. It's quite fascinating. So that's what a sequence is. And often when we talk about sequences, we like to think about how you can use them in conjunction with other things. Now, often when you're given a sequence of numbers, like some of these, notice these ones weren't really hard to guess what they were before even I gave you the names of them. So if I just blocked these out, you'd be able to guess what those are. I'm going to include in my notes some tips for trying to figure out patterns for so-called the general or explicit term. So this is the one that dictates each one of the terms. This is actually this right here. Each one of these, it gives you a formula for how you can get any arbitrary term in the sequence. So there's all sorts of different kinds. A couple tips I can give you is look for a pattern. So the first thing is identifying a pattern for the first time will get you one step closer. And once you start realizing you're looking at something that reminds you of something, just turn it on its head. So there's all sorts of different ways you can express these. If there's more interest in sequences, I can more than happy to talk more about them. You can create all sorts of different kinds of sequences. For example, so-called alternating sequences. That is another thing that exists. And if you could recognize patterns like these, it makes things a little easier. So actually, I'll do one example here. Let's consider an example here. And I'll give you my second tip. So suppose I give you a sequence that looks like this. 1. The second term is going to be -1/4. Third term is going to be 1/9. Fourth term is 1/16. Fifth term is going to be 1/25. The sixth term is -1/36, and so on. Now, to be the most truthful with you, technically speaking, if you asked me to guess what the function is, the sequence is, there's ultimately not a one true answer here, because somebody could easily conceive of a sequence where, say, the parts that I haven't shown you here might be something else. But normally we take on the description itself that I have here that this is indeed going to be some pattern that we're trying to get a general or explicit formula for. So I want to walk you through kind of this process. So the first tip I gave you is look for a pattern that you recognize. Now I must stress that humans, we love looking for patterns, but we're also really bad at overgeneralizing patterns. So take caution to the wind that we sometimes see things that aren't there. So we have to be very careful, and that's why we have the dreaded M word, the mathematics, and the mayonnaise mustard. A really good sandwich. That's why we need this stuff. Because we're not really the greatest at spotting this stuff right on the hoot. Is that it's very easy to deceive ourselves when we start seeing things like this. That's why this stuff is pretty helpful. So the other tip I want to give you is try to relate the terms for the indices with each other. So it's a very powerful and useful tip. When you're trying to identify a pattern, associate the terms in that pattern with what you see in the sequence. So the first thing you should notice here is there's two things. Well, if I were to let me just make it a little easier for you to see what's going on here. Possibly. I'm going to write it like this. Does anything here look awfully suspicious to you? Let's not worry about, because like I said, we're going to start by just trying to find a pattern. So first, I'm going to write it like that to make it a little easier to see, because 1 is in fact 1/1, right? Okay, the next thing I want to do is I'm going to ignore, because I'm not quite sure how to do it yet. I'm going to ignore these negative signs. So far, if I look at this, what does this remind you of? What number sequence does this remind you of? I'll give you a hint. We've seen it not that long ago. So I'll give you a tip. So if I give you 1 bottle, I end up with 1 bottle, right? If I give you 2 bottles, I should get 4 bottles, and so on. So what exactly are we dealing with here? So another tip I'll give you. Ignore the fact that these are all 1 over or something. Just look at the somethings. What are these things down here? Ignore the numerators. Just ignore them all. Yeah. It's our square numbers. Exactly. Somebody's got it in the chat. Awesome. It's the square numbers. So you can see right now you're just looking at the square numbers. So we know that if we're going to write up a general term, so imagine you have this, so an arbitrary term of my sequence, we know it's going to look something kind of like this. So we know what the square numbers look like. This is what the general or explicit formula for the square numbers would look like, right? And this would be for for every k greater or equal to 1, right? So far we got something we're starting off with, right? So first, if you're not sure what to do with it, just simplify down a little bit so you can see what pattern you want to get. So far we know this. So far we got something that looks kind of like this if we ignore the negative signs, right? So far we're really close here. So if I ignore the negative signs, notice if I put in 1, I get 1 over 1 squared, which is 1. 2, 1 over 2 squared is 4, and so on. Now we got one little detail to deal with, those darn negative signs. Now I'm going to introduce you another mechanism that very often pops up in sequences and series analysis, very, very often. It's our friend the alternating sequence. So a tip I can give you again is if you ever need to kind of go back and forth between positive and negative, if you have if you need the ability to kind of flip it from positive to negative, flipping that sign, your best friend is to use this. Or let me just put a K here, because we're using K. So if I were to, so notice that if I use -1 to 1, that's just -1, right? But what happens when you square a negative like this? So if I had -1 squared, what happens? Is it still negative or does it become positive? It's the same sign, different sign? What happens? It flips it, right? So now, if we think about that, that's rather interesting, right? So this will give us a mechanism for getting our negative sign, then a positive, but I don't think it's that easy, right? We have to be a bit careful about this. So imagine if we put that in here. Let's put this literally right there. Let's try putting this in like this. And let's see if we get that sequence up there. So if I put in 1, I get -1 to the 1, which is -1 over 1 squared, which is -1, right? That's not quite right. We need to remember, got to use my second tip here that I suggested. Associate what we're dealing with the index. So notice that the first index is always, this first one is going to be positive. Then this one's negative, then that's positive, then negative. Notice that every odd term in the sequence, every one of those is always going to be positive. Every even one is going to be negative. So if I just put in 1 in here, that's not going to cut it. I need it to be positive. So here's a tip. I'm just going to add 1 to that. Because remember, it's -1 raised to an exponent. It's not going to magically turn into some massive number, right? It's just going to be -1 or +1. But notice if it's 1 plus 1 here, this will become -1 squared, right? Which that'll get us just 1. Pretty fascinating stuff, right? So this is actually a nice little show of how you can actually create a general or explicit formula for this sequence. So hopefully you thought that was kind of neat. Ah, that's a good question. So could you put a whole negative sign in front of this thing? Now, the one thing we have to be a bit careful. See, I don't ever want to exclude anything. That's a fair question, right? So if we tried putting a negative out front, we need some. So keep in mind, I could put a negative out here. That's actually a good point. We could do that. So if you're actually thinking about this, if I need to flip it and then flip it again, so I can go like, I don't know, let's try like do like this. But we need this like all in parentheses, I think. Let's see. I like to play around with this with you guys. So let's see, we got minus, so if I have -1, that gets us just 1, right? So if I make sure that it's negative in here, then this becomes positive. Very slick, I like that. I think this also works. I want you to try thinking about that. I think that actually works. But yeah, no, this gets you thinking, right? So the whole idea here is just is to try to look for patterns you recognize first when you're trying to come up with an explicit or general formula. And I must stress that this isn't by any means just easy all the time. You don't just see it right away. Very often it's just like, okay, I know that number sequence. So I'm just going to try playing around with that. So like I said, one thing, if you find yourself fiddling around, you're just like, hey, look, I'm just kind of bored today. I'm going to go look at funky number sequences out there. This website is your best friend. And that's an I, by the way. There's an I. This is an I right here. You can, like I said, if they still have the feature on that site where you can make it play MIDI versions, like straight up like keyboard-esque tunes of the integer sequences, you could do that on that site. It's pretty neat. But yeah, hopefully you thought that was pretty interesting. So the whole idea is to derive a good guess of what you're up to. And you might ask, Dan, how do you exactly check this thing? You could, of course, also... Actually, I have another version of way of writing this, so there isn't just one way of doing this, by the way. Here's another one. I was about to get to my next thing, but I also was going to mention this one. Here's another way I could reformulate the same one. So we have, so far, 2 different ways of doing it. Here's a third one. So I'm going to do... let's see. Yeah, let's do this one. So I'm going to have minus 1 to the k over k plus 1 squared. But the thing is, we're going to change how we vary k. So we're going to start k at 0 now. So notice that if you start k at 0 here, we're always bumping up k up by 1 here. So notice that all we're doing is just nudging it a little bit in one direction to make it so it squares it. I like to think of it kind of like a little like work line. You're just like, okay, just a gentle push, gentle push. There we go. So here we go. So, but yeah, no, so like the main point I'm getting at is there's not just one way of doing it, but most certainly you'll find that there's a little bit of creativity that goes into this process. And I tried to give a couple of tips here.